In the previous section, we saw how to deal with inequalities when the variable of the inequality is being multiplied by a rational number or being divided by a whole number. Either way you want to look at it, it actually means the same thing. And we did that by dealing with the inequality in the similar manner that we did with dealing with linear equations. We simply multiplied by the reciprocal. Well, here we're going to deal with inequalities where the variable is being multiplied by a whole number. So let's see how to solve these. So we have the first one is 3x is greater than 6. Well, if this was an equation, if this was an equal sign, we would isolate our variable x by dividing both sides by 3, which will, in essence, cancel these 3 out, and we'd have x is greater than 2. And that's our solution set for this particular inequality. All right, so we see that inequalities tend to work the same way in most cases as equations. So let's take a look at a few more and see if this holds true. Let's say we have 2x is less than minus 12. We simply solve for x by dividing both sides by 2, the coefficient of x, which gives us x is less than minus 6. So there's our solution set. Not a whole lot to it. Let's look at a few more. We have 10x divided by, greater than or equal to 20. All we simply do is divide by 10 on both sides, which cancels these two terms, and we have x is greater than or equal to, cancel these zeros, x is greater than or equal to 2. So that means our solution interval is the set of all values for x that are greater than or equal to 2. So we can plug in 2 into our inequality, and this would still hold true. We can plug in any number greater than 2 into our inequality, and our inequality should remain true. Should be a true statement. So let's look at a few more examples just to get some more practice in. Let's say we have 8x is less than or equal to a minus 32. Well, we simply isolate our variable by dividing both sides by 8. That cancels these two terms, so we have x is less than or equal to a minus 4. And that's our solution interval. Let's look at the next one. Let's say we have 5x is greater than 75. 5x is greater than 75. All we simply do here is divide both sides by 5. These two terms will cancel, so we have x is greater than 15. Now what this solution interval means is that we can plug in any number greater than 15 in for x, and this should actually hold true. So let's go ahead and prove this. Let's plug in 20. 20 is greater than 15, so let's plug in 20 for x. So we have 5 times 20, it's plugging into our original inequality, is greater than 75. 5 times 20 is 100. We still have greater than 75. 100 is definitely greater than 75, which means it checks out, and this is indeed the appropriate solution interval for this inequality. All right, so we can always check these by plugging back in and see if the inequality remains true. Very simple, similar to checking equations. So let's do one more. Let's say we have the inequality minus 6x is less than minus 30. All right. Well, when we're solving equations, we simply divided by minus 6. We divided by a minus 6 because we want to solve for a positive x. We want x to be positive, so the minus signs and the coefficients cancel, which gives us x is less than, these two negatives cancels, x is less than 5. So if this is our solution interval, we can pick any number that's less than 5, and we can plug it back in for x, and this inequality should hold true. So let's go ahead and do that. Let's pick a number that's less than 5. Let's just say 0. Zeros are very, very much easier to work with than any other number. So we have minus 6 times 0. We're plugging in 0 for x because 0 is less than 5. So minus 6 multiplied by 0 is less than minus 30. This is our original equation, just zeros plugged in for x. Minus 6 times 0 is just 0. So we have 0 is less than minus 30. We have a problem here because this isn't true. 0 is not less than minus 30. So this inequality is not accurate. 0 is greater than minus 30. And so we need to come up with a certain rule when we're dealing with division by a negative sign. And we can see it by constructing to the side just a very simple example. Not to insult your intelligence, but we know that 1 is less than 2. Now if we multiply both sides by -1, the same thing as dividing by a negative sign, we would get -1 is less than -2. Okay, now this is interesting because we know that -2 is less than -1, not greater than. So how we're going to deal with this is whenever we're multiplying by a negative number or dividing by a negative number, we need to flip the sign, flip the inequality sign. So if we flip the sign here, when we multiply through by a -1, we're going to get -1, and we're going to flip this less than sign into a greater than sign. -1 times 2 is a -2, and that actually holds true. -1 is greater than -2. All right, so let's prove this. Let's redo our example up here using this rule and see if it works out. So we have our original example. Our original inequality is -6x is less than -30. So let's go ahead and again divide by -6. These two terms cancel, so we're left with x, and let's go ahead and flip the less than sign into a greater than sign. These two negatives cancel, so x is greater than 5. So now we have a different solution set than we did up here. We had we have a less than sign when we divided by -6. Here we have a greater than sign because we just flipped the sign. We want to see if that's true, so let's go ahead and prove this. Let's pick out a value for x that's greater than 5. Let's just go ahead and say 6. 6 is greater than 5, and plug it into our original equation. So we have -6 times 6 is less than -30. Let's go ahead and see if this is true. We're plugging in a number greater than 5 into our original equation and seeing if it holds true now that we're just flipping the sign. So we have -6 times 6 is a -36 less than -30. And this checks out. -36 is less than -30. So we're addressing here a very important difference between solving inequalities and solving equations. When we multiply by a negative number or we divide by a negative number, we need to flip the sign of the inequality. So if we have a less than sign, we need to flip it into a greater than sign. If we have a less than or equal to sign, we would have a greater than or equal to sign right here. All right, so we'll look at several more of these examples in the next section. We want to do a whole section just on these type of examples because this is extremely important because we'll be solving quite a few inequalities in the future. So I'll see you in the next video.